Look at the device you're using right now. The processors inside rely entirely on our ability to control how electrons move at the microscopic level. This control comes from condensed matter physics. It gives us precise equations that map exactly how particles behave in a material, allowing engineers to build semiconductors, supercomputers, and the entire digital infrastructure of the modern world. But for all of its predictive power, condensed matter physics has a blind spot. It can tell you how electrons flow, but it cannot explain why the mathematical equations that govern them take the specific forms they do. We have constructed a global civilization using rules that we know work perfectly, without actually understanding where those rules come from. That blind spot becomes glaringly obvious when physicists look at advanced quantum materials, like twisted Mo-T2 and rhombohedral graphene. This chart shows electron energy states in these materials. Instead of a continuous curve, they lock into isolated plateaus at specific fractions, 1/3, 2/5, and 2/7. Standard theory treats these as mathematical artifacts, offering no structural reason why these particular fractions appear. Those specific denominators represent a literal shadow cast by a physical geometry underneath the material. Decoding why these specific fractions show up in the lab is the key to tracing the rules of quantum mechanics back to their geometric source. We start with a single physical postulate. Time is not an empty background. It is a one-dimensional string, and that string is under absolute tension. Because time is under tension, it resists displacement. When any mass or particle exists in space, it is physically pushing against that tension substrate. Just like a guitar string, the time string deflects into a precise parabolic curve. An electron's wave energy must wind inside that space and perfectly close end to end. If it spirals without closing, the waves destructively interfere, instantly canceling to zero. Matter doesn't exist by chance. It only survives if it passes through a strict geometric filter, where only perfectly closed paths are allowed. When you force a parabolic wave to close on a circle, the geometry forces a very specific number. The boundary creates exactly 30 equal steps, acting as a sieve. Wave modes sharing a factor with 30 cancel out. Only the 8 coprime numbers survive: 1, 7, 11, 13, 17, 19, 23, and 29, forming stable electron lanes. An electron isn't randomly picking its behavior. Its flow is strictly dictated by the allowed lanes of this modulo 30 geometry. Which brings us back to the twisted graphene in the laboratory and those bizarre fractional states of 1/3, 1/5, and 2/7. The physical denominators observed in the lab, 2, 3, and 5, exist solely because they are the exact prime factors of the number 30. But that leaves one outlier: 2/7. 7 is not a prime factor of 30. To find the 7, we look at the 8 surviving coprime lanes. If you calculate the total field amplitude transmitting through those 8 lanes, the exact geometric sum is 7/2. This is the Noether charge of the system. In this geometry, filling a state means taking one discrete step within that total field. Since the total charge is 7/2, a single unit step is the reciprocal of that value, exactly 2/7. The data points on the chart are not abstract artifacts. When physicists measure those fractions, they directly observe the prime factorization of the modulo 30 geometry. This framework offers a specific testable prediction. Because the 2/7 state comes from an integer step of the Noether charge, and 5/7 comes from a half-integer step, the geometry demands a measurable difference in stability between them. There must be a distinct particle-hole asymmetry, meaning the gap ratio between those two states will be unequal. The standard composite fermion picture assumes all of these states are dynamically equivalent, predicting perfect symmetry between them. A precision transport measurement of that gap ratio will prove which model reflects reality. The mathematical rules governing electrons are not random. They exist because the universe forces waves to fit inside the deflected tension of time. The mystery of why is finally answered.